Bright QT. Every student matters.
Now, let us take something different. How? Instead of taking one circular loop, let us take a wire having many loops. And now, let us connect this wire with the cell and plug the key on. This is the positive terminal, negative terminal. The current will pass from here. Importantly, in this particular part of the wire, the current is going in the downward direction. In this part of the wire, it is going in the upward direction. Again, downward direction, upward direction, downward direction, upward direction, and throughout. Right? Now, importantly, these loops are so close to each other that we will almost get a complete mess of magnetic field lines overlapping each other. Let us see. Fine. This part of the wire, we will see the magnetic field lines like this. Current was going downward, so the magnetic field lines will be in the clockwise direction. In this part of the wire, again we will have magnetic field lines, which will be, because the current going upwards, it will be opposite to the direction of clock or anti-clockwise. Here again we will get magnetic field lines clockwise. Here we will get magnetic field lines anti-clockwise. Here magnetic field lines concentric circles clockwise direction, anti-clockwise direction, clockwise direction, anti-clockwise direction. Similarly, we have throughout magnetic field lines, and not only this, of course, this part also has these kind of magnetic field lines. So you see, with the same blue color, we see that the magnetic field lines are overlapping each other, right, to a great extent that it has become a mess altogether. Now, when these anti-clockwise, clockwise, anti-clockwise, clockwise throughout this particular coil, right, we see that it is clockwise, anti-clockwise, and when we observe, we find a very unique and strange and remarkable observation. That is, when I see this particular wire in totality, like this was my initial wire with loops. Fine. This is a cell or a battery and a plug-in key, plus minus current going on. A very unique observation was that this particular coil as a whole behaved as a bar magnet. When I talk about behaving as a bar magnet, I am saying that one of this particular coil's end will act as a north pole and the another will act as a south pole. And just like a bar magnet, the magnetic field lines will be like this. Fine. How? Let us see. The magnetic field lines will be like the ones we find in a bar magnet, and the direction in totality as a whole, when we will see that the direction is from north to south pole, again like a bar magnet outside the coil I am talking about. Fine. So this kind of setup is given a special name. This is known as solenoid. Very, very, very important, dear students. You need to practice this diagram from the book. From exam point of view, this question is very important. You will be asked to make a solenoid or write a short note on solenoid with figure or diagram. Right? In this diagram, you need to first of all take care of this plus minus. Your plug-in key should be on. The direction of current arrows should be shown, and here you will be showing the coil, circular coil, and the magnetic field lines. This north pole and south pole should be specially given attention to. Right? They are quite important to write, the north and the south pole. The direction with the arrows you need to show. This is a solenoid, and this solenoid is defined as, you should know the definition of a solenoid. The solenoid is a large coil. It's a large conducting wire having a large number of circular turns in it. So a copper wire is taken preferably as a solenoid. Copper is a good conductor of electricity. A large copper wire, insulated copper wire having a large number of turns in it connected to a battery is known as a solenoid. Fine. Now in this solenoid we have seen quite important 2 or 3 things that you need to remember. First thing we saw that this solenoid acts as a bar magnet. This is the first thing, right? And as per a bar magnet, the magnetic field lines were going from north pole to the south pole outside the magnet, outside the coil. I am talking it about outside the coil again and again. Why? Because now you need to relate a very important thing, that is that inside this coil, when I am talking about this coil, the inside magnetic field lines, there are 2 important observations. One is the direction is from south to north. So very important, inside the coil, the number of turns that we have taken inside the coil, we see that the magnetic field lines are going from south pole to north pole. And second very important thing is that the magnetic field lines are parallel to each other inside. They are parallel to each other inside the coil, and this parallel to each other signifies a very important thing, that inside the coil there is a uniform magnetic field. Because if the magnetic field lines are parallel to each other like this, that means the effect of magnetic field lines at any given point in this area is equal because they are parallel. So the parallel magnetic field lines signify that this is a uniform magnetic field. This is a 1 mark question that may be asked to you. You will be asked to draw a uniform magnetic field. Now a uniform magnetic field, how it will be represented? Simply you have to just make 5 or 6 parallel lines. That is not all. Another thing is you need to mark south, north, and the direction should be from south to north. This is a uniform magnetic field which is found inside a solenoid. So this solenoid is very important. I again repeat, the diagram with all the labelings, especially the arrows, they need to be taken care of. Secondly, how to form or represent a uniform magnetic field. And this is the most important observation that we saw in a solenoid. What? That as a whole, solenoid behaves as a bar magnet with one of its pole as north pole, one as south pole. Secondly, the magnetic field lines are going outside the solenoid, north to south, and inside, south to north. Third thing, the inside magnetic field lines are parallel to each other, signifying a uniform magnetic field. Got it? Now, we have talked about the straight current carrying conductor. We have talked about circular, and same way we will talk about what? The strength of magnetic field. There are again the factors affecting the strength of a magnetic field produced by a solenoid. Right. Now, in case of a solenoid, the first important factor, as it always has been, is of course the amount of current. And the magnetic field is always directly proportional to amount of current. That is, the more is the amount of current, the stronger will be the magnetic field. The second factor here is the number of turns. The magnetic field is directly proportional to number of turns of the coil. Why? Because in one coil a magnetic field is produced, and by increasing the number of turns the magnetic field produced is multiplied. So the more is the number of turns in the coil of a solenoid, the stronger magnetic field will be produced. Because these turns, as the number increases, they get closer to each other, and in the same wire, if we increase the number of turns and make them closer to each other, then of course the magnetic field lines produced will be closer, and hence stronger will be the magnetic field. Got it? Fine. Alright. Now in this circular wire there is one clock rule that you need to relate. What does this clock rule actually say? In the straight current carrying wire, whether it was in this vertical, horizontal, both direction, horizontal or in vertical, we saw that the current is going either from west to east or east to west, upward or downward. We found the direction of magnetic field lines with the Maxwell's right hand thumb rule. But in case if there is a circular wire like this, right, now in this particular part we can individually we can say that the magnetic field lines upward hai. In that case, current going upward, it will be anti-clockwise, current going downward, it will be clockwise. But what about this particular front face of the magnet, of the coil, sorry? If the current is going either like this in this direction, or let us take in this direction. Now we have changed the direction. Here the direction is clockwise. It is going in the clockwise direction, and here the direction is anti-clockwise. If I want to know this particular front face of this wire, which particular pole it will be, north pole or south pole, that is found out by the clock rule. Now what did this clock rule say? That if this particular current is going in the clockwise direction, then the south pole will be seen in the face of the wire, and if it is anti-clockwise, it will be the north pole. Now there is a simple trick to remember this thing. Just for south pole we will make this S, and for north pole we will make this as N. Right. Now what we will do is, the way we are making this N, right? So this is the direction like this, right? Going into this direction, I am making this like this, and the way I make the N, all of us almost make the N like this only. First this part, then this part, and then this particular part. This is going in the anti-clockwise direction. So anti-clockwise direction, if the current is going, the face of the wire will be north pole, and if it is a clockwise direction, it will be a south pole. Got it? Fine.